Today's lesson is about apportionment, which essentially means a fair way to divide something up that isn't money or maybe like a thing like a house or a boat or a car. You can read the top paragraph, and it talks about how we decide how many votes every state gets in the electoral college. And this is mainly based on population, and there's a set number of seats. So the first thing we want to figure out is, what is each representative or each seat? How many people does that represent? And we call that the ideal ratio. So the way we will find the ideal ratio is finding the total population divided by the number of seats. Sometimes you're not given the total population, in which case you just need to sum together all the small parts. Like down here, we have classes. Even though it gives us 1019, if we wanted the total, all we'd have to do is add up all the classes. Now it's important you understand that this ends up being a ratio, which stands for, let's use our example we're about to talk about, which is students in the student council. This would represent students per seat. Okay, so let's look at our example. It says that there are 1,019 students and 30 seats on the student council. So the ideal ratio would be 1019 divided by 30, which is a rounded figure, gives us about 34. So what the ideal ratio is telling us is that there are 30 seats, and each seat represents 34 students. So then we want to figure out, well, what is the quota per class? And the quota means how many sets of 34, or what's the population divided by the ideal ratio. And by finding this, we're saying how many sets of 34 are in our population, i.e., how many representatives should that group get, that state, that freshman class, etc. So when we find this, we find that 319, 240, 252, 208, all divided by 34, give us these values. And when you're finding a quota, go ahead and find, 2, 3, 4 decimal points, because we are going to use those decimals later for something called the Hamilton apportionment. But to begin the problem, we're just going to say truncate, which means to ignore the decimal part. That's truncate. Ignore the decimal part of the number. And this gives us 9 seats for the freshmen, 7 seats for the sophomores, 7 seats for the juniors, and 6 seats for the seniors. Now, this is a really good start, but if you add all this together, we're going to get 9, 16, 23, 29 seats, and we still have one more to give away. This is where apportionment comes into play, and there are 4 methods that we'll talk about how to figure out who gets that extra. The Hamilton method awards the remaining seat to whoever quota had the largest decimal point. So when we ignored those earlier, that was just a starting place. Now I look, okay, 38, 6, 41, 12. 41 is the most, so they get the extra. So my final total here is 8 for the juniors, and now I've given away all 30 seats. If there were 2 extras, let's say after we found our quotas we got to 28 seats, then we'd have 2 extras, and it would go to the top 2, which would be the juniors and the freshmen, because 41 and 38 are larger than 12 and 6. Since we only have 1 extra, then we're done with this problem. Moving on to what we call the Jefferson method, before I go to the other side, what we have to understand is up to this point, finding the ideal ratio and the quotas is all the same up until we figure out there are only 29 left over. 29 counted for, 1 left over. So then the Jefferson method has a different way to assign this extra 1. The Jefferson method is an ideal ratio where we are fiddling with the divisor. And you can read all through these steps, but basically what would happen is, 1, you would find your ideal ratio. 2, you would find all your quotas. 3, you would truncate, just like we did on the other side, to get these values. So these are all the same as the Hamilton method. It's just that we now have a new way of figuring out who gets this extra 1, because again, remember, this adds up to 29, You need to give away one more. So how this is figured out is we find a new adjusted ratio for each class. We will take the population of the class and the number it got, so the freshman got 9, and we're going to add 1 to it. And you see up here I have a kind of a formula that says class size divided by truncated quota plus 1. So then here would be the sophomores had 240 people. Remember, they got 7 seats, so now they get 8. 7 plus 1. Same is true here. They also had 7. 7 plus 1. And then 208 divided by 6 plus 1, or 7. Now in your calculator, make sure you either decide that this is 319 divided by 10 or use parentheses. Otherwise, what it'll do is it'll divide by 9, give you an answer, and then it'll add 1 to it, rather than dividing by 10. So here I get 31.9, 30, 31.5, and lastly 29.7. And since we only have 1 extra, it'll go to the largest adjusted ratio. So we are not looking at the decimal part like we did with the Hamilton method. We are completely looking at the whole number. So between 31.9, 30, 31.5, and 29.7, this is the biggest. So the new breakdown would be that the freshmen get that extra. And my answer is 10, 7, 7, and 6. If you have any questions, let me know. This is the first section where we talk about 2 of the apportionment methods. There are still 2 more called the Webster and the Hill method that we'll talk about next time in class.